Okay, so previously we had discussed the infinities, and now this is an introduction to analysis. And our first chapter in this in this uh, analysis thing is bounds. So in the final three chapters, there are only three chapters remaining in the book of Introduction to the Pure Mathematics. We are going to talk about a topic with a different flavor from the rest of the book. And this is a topic called mathematical analysis, or just analysis for short. This is a huge area which, at an undergraduate level, starts off with the study of real and complex numbers and functions defined on them. Of course, we can't cover very much of the subject, but this would require several more books. But we will do enough to prove several interesting results, such as putting the existence of decimal expressions for real numbers on a rigorous footing and proving the existence of nth roots of positive real numbers. Okay? Before we can start studying functions of real numbers, we need to go more deeply into some basic properties of real numbers themselves. And that's what we will do in this chapter by defining bounds. So, to define bounds, is the ba- is the this chapter is based on the theory of bounds for sets of real numbers. So let's give the definition. Let S be a non-empty set subset of real numbers. So S is a set consisting of some real numbers and S is not empty. Okay, we say that a real number U is an upper bound for the set S if the small s in S is less than or equal to U for all S in S. Likewise, L is a lower bound for the set S if every element of S is greater than L for all S in S. Okay, and this is a definition where we define upper bounds and lower bounds. Perfect. Now we want to do this by an example, by giving an example. So let's give an example. The first one is, let S be a set which has 1 over n such that n is from integers which is nothing but a set which contains one half, one third, one fourth, and so on. Then, as simple as 1 is an upper bound, for the set S. So are 2, 17, and indeed any number that is 8 least 1. Okay. Also, 0 is a lower bound for the set S, and so is any number less than or equal to 0. Okay. 2. Example 2. Let's say if the set S is the integers, then S has no upper or lower bounds. Three, if the set S has elements X such that X is a rational number such that the square of X is less than 2. Okay. Then under root 2 is an upper bound for the set S, and under root minus under root 2 is a lower bound. Now, you can see upper and lower bounds need not to be the elements of the set itself. Okay. As we see from these examples, a set can have many upper bounds. It turns out to be a fundamental question to ask whether all the among all the upper bounds there is always a least one. Let us first formally define such a thing. So let's write that question also. Among all the upper bounds, is there always a least one? And to answer that, we need a definition. For least and greatest lower bound. Okay, so we say late is be a non-empty set. The even subset of real numbers, and suppose the set S has an upper bound. Now we say that a real number C is a least upper bound for the set S as LUB if the following two conditions hold. Which one? Number one is C is an upper bound for S, and number two is if U is any other upper bound bound for S, then U is greater than or equal to C. Similarly, D is a greatest lower bound, which is GLB for S if the condition one is D is a lower bound first, and if L is any other lower bound for S, then L is less than or equal to D. Perfect. Now let's define these with an example. So the example would be that S is a set which has same elements 1 over n such that n is from natural numbers. We claim that that 1 is least upper bound for S. To see this, observe that 1 is an upper bound and any other upper bound is at least 1, since 1 is an S. So observe, to see this, 1 is upper bound and any other upper bound is it least one, since one is in S. Okay. We also claim that zero is a greatest lower bound for S. This is not so obvious. First, 0 is a lower bound. And let L be another lower bound for S. If L is greater than 0, then we can find n in N such that 1 over N is less than L, but 1 over N is in the set S. So this is not possible as L is a lower bound for S. Hence, either L is less than or equal to 0. Okay, and this proves that 0 is a greatest lower bound. Now, it is an absolutely fundamental property of real numbers that every set which has an upper bound also has a least upper bound. We won't prove this here. It is relies on a rigorous construction of the real numbers, which we have not done. It is not. It is known as a completeness axiom for R. Now we will just state that every set which has an upper bound also has a least upper bound. Okay. Now let's talk about the completeness axiom. Let S be a non-empty set. Subset of R. 1. If S has a lower bound, then it has a greatest lower bound. 2, if S has an upper bound, then it has a least upper bound. For interested readers, you can search out this and think about it more. If S has a lower bound, least upper bound, it is easy to see that it has only one least upper bound. We leave this to the reader, so it makes sense to talk about the least upper bound of S. We sometimes done this by LUB of S. Likewise, a set S with a lower bound has only one greatest lower bound, denoted by GLB of S. As we have said, the completeness axiom underlies the whole of the theory of real numbers, and you will see it used many times in your future study of mathematics. In the next two chapters, we'll apply it in the study of limits and functions and use it to justify the existence of a decimal expression and nth roots. For now, here is a little example to give you a flavor of how the axioms can be used. So let's try to use them. This would be a long example, but to give you a flavor, let's try to do that. So this is example 22.3. So you see we saw in chapter 2 how to prove the existence of a real number under root 2. And more generally of under root n for positive integer n. In chapter 2, we prove the existence of the real number under root 2 and more generally under root n for n in the positive integers by means of clever geometrical construction, right? However, proving the existence of the real cube root of 2 is not so easy. In this example, I'll show you how to use the completeness axioms to prove the existence of. So now, using completeness axiom, we prove the existence of cube root of 2, which is 2 power 1 over 3. Okay. The key idea is to define the following set of real numbers. Or define the following set of real numbers S, which has x in x, such that x is a real number, comma, x cube is less than 2. Okay. Thus, S is the set of all real numbers whose cube is less than 2. First note that S has an upper bound. Upper bound. For example, 2 is an upper bound. Two is upper bound since if x cube is less than 2, then x would be less than 2. Therefore, by completeness axiom, as has an least upper bound, and say that C is a least upper bound of the set S. Now we shall show that C cube is 2. We shall show that C cube is 2. We do this by contradiction. Now, by contradiction, assume that C cube is not 2, then either C cube is less than 2 or C cube is greater than 2. We consider these two possibilities separately in each case, obtaining a contradiction. So case 1, is C cube is less than 2. Our strategy in this case is to find small number alpha greater than 0 such that, so we need to find a small number alpha greater than 0 such that C plus alpha whole cube is less than 2. This will mean that, and this means that C plus alpha is in the set S, whereas C is an upper bound for S, a contradiction, where is C is an upper bound for S, which is a contradiction. Okay, so to find alpha, to argue as follows. So to find alpha, we argue as follows. Also, I have chosen to present the steps in reverse in order to make it clear how the argument was found. We have c plus alpha cube is less than 2. But c cube plus 3c square alpha plus 3c alpha square plus alpha cube is less than 2. Now this implies, the latter term implies this. And then again, this previous one is implied by this 2 minus c cube is greater than 3c square alpha plus 3c alpha square plus alpha cube. And this is also implied by 2 minus c cube is greater than alpha 3c square plus 3c plus 1 and 0 is less than alpha is less than 1. The last inequality follows since the last inequality follows since 0 is less than alpha is less than 1. We have alpha square is less than alpha and alpha cube is less than alpha. Since 2 minus c cube is greater than 0, we can choose alpha such that we can choose alpha such that 0 is less than alpha is less than 1, and alpha is less than 2 minus c cube over 3c square plus 3c plus 1. Then, by the above implication, it follows that c plus alpha cube is less than 2. This leads to a contradiction. Contradiction as explained before. Now, we have case 2. And then case 2 says that c cube is greater than 2. Now in this case, our strategy is to find a small number beta. Find beta greater than 0 such that c minus beta whole cube is greater than 0. Sorry, 2. Still. Now if you do this, then for x in S, we have x cube less than 2, which is less than c minus beta whole cube. Hence, x is less than c minus beta, and so c minus beta is an upper bound for s. However, c is a least upper bound of s. So this is a contradiction. To find beta, c minus beta cube is greater than 2, and this is implied by that c cube minus 2 is greater than 3c square beta minus 3c beta square plus beta cube, and this is implied by c cube minus 2 greater than beta into 3c square plus 3c, minus I think this is plus 3c plus 1, and 0 is less than beta, beta is less than 1. Since c cube minus 2 is greater than 0, we can choose beta such that 0 is less than beta, beta is less than 1, and beta is less than c cube minus 2 over 3c square plus 3c plus 1. Then, by contradiction, by the above implication, actually, then by the above implication, follows that c minus beta whole cube is greater than 2. This leads to a contradiction. Thus, we have reached a contradiction in both cases 1 and 2, from which we have concluded that c cube is 2. In other words, c is the real cube root of 2. C cube is 2. Hence, we have just shown that this is the real cube root of 2. You can see that the calculations in this example are both tricky and tedious. So in chapter 24, we shall prove a general result, the intermediate value theorem, that makes this kind of argument easy, smooth, and free of tricky or tedious calculations. Thank you so much. See you in the next chapter. Please do like and subscribe.